Welcome, everyone, and thank you for joining this event of Young Cyclic. As there are a couple of people who have just joined us, as I've seen in the room, I have to repeat a few housekeeping rules. So there is no fire alarm drill planned for tonight. So if you hear the fire alarm, please exit from one of the two doors you see in this room, the back and the front. And tonight, we have invited here with us Numan Aloko to give his insights from his recent experimental study on cyclic axial behavior of build-up cold-form steel columns, which was funded by our second fund, 2023. Numan Aloko is a PhD student at the School of Civil, Aerospace and Mechanical Engineering at University of Bristol, working on cold-form steel structures for the application of rapid and sustainable construction under the supervision of Dr. Rafael Derisi and Dr. Flavia De Luca. He received his BS from Ege University in Turkey and his Master of Science in Structural Engineering at UITM in Malaysia. So without further ado, I will now hand over to you, Numan, to begin the talk. Thank you.
Okay, thank you so much. Hello, everyone. Thank you so much for joining the presentation. Tonight, I will talk about my research at the University of Bristol. The title is Cyclic Axial Behavior of Build-Up Cold-Form Steel Columns. The agenda for today, first I will define what is cold-form steel, so it may be new for some of you. Why CFS, why you are using these materials. Application of CFS framing in construction, and also its lateral load resisting system of these building types. And our research, cyclic axial behavior of build-up columns, and finally results and conclusion. So as structural steel, we have two types of steel members. One is hot rolled steel members that we are most of us familiar with that. So it's a more thicker section and dense sections. But we have also cold-form steel members that are also known as thin-walled or light gauge steel. So the cold implies here that in the process of the shaping of you can see the shaping of these sections, there is no need for extra heating. So just these machines are used for giving the shapes of these sections. So it can be used any types of section, and it can be the length of the elements will be adjusted here in this machine. So we have these C sections and Z section and U section that's traditionally was using, but nowadays we have these most optimized sections that we have the stiffeners at the web and also at the flanks. CFS have some advantages that can be useful in the sustainability application of construction, such as lightweightness. They have high strength to weight ratios compared to other materials, have recycled content up to 42%. So this values climbed by the suppliers of these materials in the UK, and also have low waste generation at manufacturing and site levels, and also reduced transports from site to site, and also fewer operatives on site, and also speed of construction. This is because this type of construction is dry line, so there is no need of formwork, and it's also don't depends that much on the weather conditions. Without extreme weather conditions, it can be the construction can be continued, and also it has a high circularity. It can be demounted and also can be reused and recycled again. But as we know, steel is not sustainable materials due to they have these high carbon emissions. So according to the two suppliers of this steel in UK, like Hadley and Metsec, so according to the EDP report of these suppliers, for example, 1 kg of cold-form steel have 2.82 carbon emission of global warming, and also Metsec have shown 1.99. But at the same time, they also now offer this lower embodied carbon steel from the same suppliers with less carbon emission, like 1.25, 27, and 25. So this means they are using electric arc furnaces in manufacturing of this steel instead of blast furnaces that uses fossil fuels. So CFS application has an application in category 1, 2, 3, and 5 of modern methods of construction defined by UK government. So the category 1 means the modular buildings. So you can see one of the module made up of all the core form steel members. And it's from UK, one of the suppliers of these buildings. So it's ready for the sheeting panels and to be carried out to the site. And also we have category 2. So we have this load bearing walls panels. That's also successfully applied by British offside. So it's not quite successful. They have this type of buildings for rapid and sustainable construction, and any type of insulation materials and fire insulation can be put between these members. And also we have the non-load bearing system. So you can see in this picture. So we have different types of panels. So the main load bearing system is concrete, but all the exterior and interior panels are made from these cold form steel panels. And for category 3, non-systemized primary structure, so we have application in the portal frames and also some trusses. So it's quite flexible material, can be used with timber, with the hot rolled steel, and also with concrete, and also with these different types of slab systems. So now the question is that with these benefits of this material, can we apply this framing system in seismic areas? So according to the US, Canada, Australia, New Zealand design codes, these systems can be built up to 6-story in highly seismic zones. The primary lateral load resisting system of these are called CFS strap brace shear wall. So it has many components. So like we have this single stud. This is for gravity loading. We have tracks to align these elements and connect at the bottom and top of these shear walls. And the main yielding and energy dissipating mechanism is these straps that should be yield during the earthquake. And at the corners, we have these elements called CFS built-up columns. So these elements are under cyclic axial loading during the earthquake, when the aspect ratio of this wall is 1 or up to 1.5. If the aspect ratio increased to 2, so these elements not only taking axial loading, also bending. So for just 1:1 on 1 to 1.5 aspect ratio, so these elements are under axial cyclic loading. According to the research in the literature, so for example, Welchev and Rogers from Canada, so they did extensively research on these shear walls by 2 types of methodology. One is without capacity-based design. So they just didn't design these members, these components without capacity-based methodology, and they tested. So they have found that these shear walls don't have ductility and also energy dissipation mechanism without using the capacity-based design. So in their next stage of experiments, so when they design these elements, also all the elements with the capacity-based design, so they have found that it was working and they can dissipate energy during the earthquake. So from their research, so it's important to design these elements under the capacity-based design methodology. So it's important. So as we know, this is 2 important elements in these shear walls, and also the hold downs connected to these elements that transfers the load to the ground. So in our research, so we investigated the cyclic behavior of these built-up elements in our research. So I will share my results with this. In our experiment, so we choose these 2 types of sections that are more traditional and commonly used in the practical applications. So we have the C sections and U section combined by these fasteners. And also the specimens were 1.5 meter long. You can see all these geometric parameters of these sections here. And the fastener spacing was decided based on local bucklings, wavelength. Local bucklings happens after certain length continuously. So The local buckling was 130 for this, for example, C section. So we choose the fastener spacing below this value and also a bit more like 200 to see how it works. The critical local buckling of this section was calculated based on finite strip method. So it's there's a software called CUFISM. So it's open source software. So we can analyze these sections and found out the critical section elastic buckling. And we have estimated the compressive strength of this section using direct strength method based on American Institute of Iron and Steel. And these combined by fasteners of self-drilling fasteners. So the diameter force was 6.3. The experimental setup that we used, you can see this figure. We have used this Dartic universal machine that have the capacity of applying force of 500 kilonewton. And we applied the actuator loading from this loading cell. So the elements, specimens were attached to the machine by these hold downs. And the hold downs were connected to the base of the machine by these 20 mm high strength bolts. The hold downs were designed according to Eurocode to take account the block shear failure and also bearing failure and net cross section. And due to the thinness of these elements, so you can see there's a lot of fasteners holes here in this hold downs. The hold downs material was hot rolled steel, so to make strong, and we didn't, the damage didn't result with these hold downs. So we tested these materials in the under tensile load. So we cut coupons from flange, 3 from web and 3 from flange. And we found out that the high strength material. So the offset method, the yielding stress is 540 MPa, the average, and also nearly 200,000 MPa is the elastic modulus. And around 600 is the ultimate stress. So you can see the strain and stress curves, and the strain was recorded with this extensometer, and also you can see the coupons failures. We have used the FEMA 461 loading protocol. So it's a continuously increasing protocol. So each step have 2 cycles with the same amplitude. The ratio with this amplitude is 1.4. And we have the strain gauge plan to install for each section at the flanges and also at the webs to see whether these sections work together or not. So after testing of these specimens at the lab, so we observed this behavior for 3 specimens with various fastener spacings for the C sections. The behavior was asymmetric pinching material, the behavior. So after local buckling happened, so the stiffness and the strength degraded significantly after this point, but in tension, it continuously still was working in the tension area. So I will discuss this point in the next slide. The maximum force was for intention 370 with these displacements, and also the compressive strength was this peak points 200, 216, and 212. So our theoretical calculation was 194, so it's near to these values. And you can see the displacements difference between the compression and tension. So we have quite difference between these 2 points. And the theoretical yielding displacement of this specimen is 4.3. The local buckling type happen is local and distortional buckling. And all these damage and failure happen at the length of 1,200 mm. You can see the final specimens after the experiments. So this is local buckling of the web at the webs. So when we apply the loading, this elastic buckling happens several times. But after a certain point of this green line, you can see this buckling happen here. With continuously applying more cycles of loading after these points, the damage accumulated here, and the inelastic buckling started to appear here with these elements, and for the third was here. And after this point, we had net failure, tension failure with these holes, fastener holes with the hold downs, and suddenly this point decreased to this point. Also with this damage accumulation, so you can see there was the tearing of these rounded flanks of these webs in all of these three elements. The same happened with U sections, build-up columns. You can see the same asymmetric pinching behavior of these columns after buckling. So you can see the degradation of the stiffness and also the strength. But still, the tension was working and absorbing energy. And at this point, the same thing happened like in C section. So you can see the yielding forces are almost the same. And you can see the compressive strength is a bit lower due to U section don't have these lips. So these lips changing a lot, the compressive strength. And because of that, we have this more innovative and optimized sections to have stiffeners and lips in these areas. So by looking the same area, same length of the members, you can see the energy dissipation capacity of these specimens, U sections. For the one specimen was not joined by the fasteners, and they in the experiment they behave separately, and the damage happened at different locations of these in these specimens, and the failure mode was local buckling. So you can see the failure mode of U sections. So the same thing, you can see the buckling at the web. And after this damage happens to this local buckling at these webs, and suddenly decrease the stiffness. And we have this point again in this net section, net tension failure. And you can see the tearing of these flanges around here. And one specimen was just connected at the hold downs, but there were no fastener were used. So you can see they behaved in different locations. You can see that the damage happened at different locations. And the fasteners keep the integrity of the specimens together, but it seems that it doesn't significantly increase the loading capacity of these sections. The data analysis from the strain gauge, we can observe that both sections was effective during the cyclic axial loading. So you can see the peak loads. But we have this a bit strange behavior here. So it's likely due to this point is the cyclic, so elastic buckling, critical elastic buckling happens here. So despite the loading is in negative side, means compression, but the strain was positive. So we have the bending of the web. So it just have these positive strains. And these have the flanges and webs and also flanges. The same thing happens here for the U sections for all these strain gauge data analysis. You can see this section more worked on outward buckling, and this section more worked on inward buckling mode. Yielding point of specimens were estimated using 3 methods. The first was equivalent elastoplastic yield method. So by drawing this first stiffness to that ultimate point. So we found this point. And also by equalizing these two areas. So it's called energy absorption method. And we have this reduced stiffness by 25% that we can, and this point is called the yielding point. So among these 3 methods, so the reduced stiffness method was near to our theoretical calculations. As you can see, all is near to 4 mm. And also the yielding strength of these elements is much lower than the theoretical calculations. And we observed that during the cyclic axial behavior, only the web of the section was effective, not the flanks. And when we take the area of the webs and multiply by the MPa of that we observed during the material testing, so we got the same numbers, almost the same numbers. We also calculated the equivalent viscose damping. So by taking the maximum hysteresis loop or energy and then dividing by the triangular area of that hysteresis loop. And we got, you can see the equivalent viscose damping of C sections more than U section. And you can see also the energy dissipation of these specimens in this graph. So when the buckling happens after cycle 12, so you can see the energy dissipation, starting energy dissipation. So, and also during the test, I will also observe that after cycle 12, there was the permanent buckling at the web of the sections. And you can see just the small lips can change a lot and energy dissipations. We're also interested in this new type of section called sigma sections. So nowadays it's possible to have these innovative and optimized sections in the CFS industry. So we first, we got these specimens prepared in the lab of the University of Bristol, but as our machine capacity was 500, so it exceeded our capacity. So we had collaboration with Christian and Juan from Imperial. So they agreed to help with us with this testing of these specimens at their lab. And we send them these materials with these hold downs and with these specimens to Imperial. And they have their setup in their laboratory, you can see from here. For the first testing, they used the same FEMA loading protocol for sigma column 1. But based on their first observation, so there were a lot of damage, local damage to the other connections. So, so we have changed the loading protocol to just more work on compression, a slight in the tension, but more, mainly in the compression side. So it's a near fault protocol, and we decided this protocol for testing second sigma column. So this is the results. So this was the sigma column 1 hysteresis loop. So you can see there is very less capacity in the tension part. So during, because of this connection, local damage, and you can also see have this compression sides, but it's more stiffer than the tension side. And for the second protocol and second sigma column, so you can see only the behavior is the in compression. So it's me have this tightened up to this point and then applying load again. And for this type of section, we have much more capacity in compression and more smooth curves of hysteresis loop than this one. So this is the failure pictures from their experimental at the Imperial. So you can see this, the damage happened at the bottom of these connections. So due to the imperfections of these hold downs, so there was also movement and rotation. And so they pressed this web and it's buckled, and also we have localization of failure around these fasteners. For the second sigma column, so we have changed based on their from the Christian Malaga for their this type of experience. So they say that we should change the protocol, and also they changed the fastener connections here from restrained. They applied restrained bolted region here at the bottom and top, and they have tested these specimens, and you can see all these localized buckling again happen at the this connection parts. You can see from this picture. So as a conclusion, buckling strength was a key factor for this axial behavior of these specimens. Following buckling, so both strength and stiffness degraded significantly. Fasteners showed no sign of damage under cyclic loading. Although fasteners spacing did not increase the column strength, but it kept the integrity of the specimens together, and also always was in contact during the cyclic axial loading in the compression. Also, in the monotonic loading, based on previous literature, so the fastener and fastener spacing does not improve the sectional buckling, but it can improve the global buckling. So as our element was 1.5 meters, so if we increase the length to 3 meters, for example, so I think there will be the influence of fastener spacing on global buckling, so it will improve. When build-up columns were connected through the web using hold downs, only the web carried tensile forces after buckling. So this type of connection is applied in real application. So we don't have welding connection in the real application of these type of structures. So based on this experiment, so when the buckling happens, so only the web is working during the tensile stage of this behavior of this tensile specimens. Sigma 1 column was failed, involved local buckling in the web and also at the bottom connection, and also combination of tilting, bearing, block tearing that is declared by their report that they sent us. And also the Sigma column 2 failure was concentrated in the rounded corners. And also both columns exhibited local deformation at the connection opposite the buccal regions in the early testing stage. Axial stiffness, this was important. So axial stiffness in compression was greater than in tension. This is because the thin wall section have a slight rotation movement at the supports. So finally, I want to thank for Cyclic for their funding, and also for Albion sections for their generous support in providing materials, and also from Juan and Christian Malaga from Imperial for their helping us in testing Sigma build-up sections, and also with my supervisors. Thank you. And thank you for your attention. If you have any questions, you are welcome.
Thank you very much for this interesting presentation, Numan.
Thank you.
If anyone has any questions, please let me know. I will pass over the mic. I don't see any questions coming up in the online chat just yet, so I guess we can take some questions from the room.
Well, thank you very much. It was very interesting to see. While you were presenting, I just was thinking, are you looking in your PhD at the slenderness of the section and how that affects the behavior or not, just the cyclic behavior and the effect of slenderness if you have a thinner section, a thicker section? You mentioned something about the length of the fasteners.
Yeah, it's changed a lot with both of the global slenderness and also the sectional slenderness. So when we have this, so it was really at the beginning. So you can see both of the global slenderness here, C, sigma C, and also sigma L means local. So when there is the slenderness increase, so also the energy dissipation decreases, both with the global buckling, also with the sectional slenderness. So if you have more thin wall members, so there is less energy dissipation.
I see, and probably also the spacing of the fasteners will have a bit of influence.
So it's have effect on global buckling. So because it will provide some unit of that behave together. With the sections, we should have these more innovative sections like these stiffeners at these flanks that increases the local buckling. And when we have the sheeted panels with attached to this side, so it can increase the distortional buckling strength of these sections.
Thank you.
You're welcome.
Anybody else want to ask anything? I can ask something myself, if you don't mind. So I noticed that you use a lot of fasteners and also like for the hold down purposes, like steel base plates and fasteners again. So I guess this is a relatively thin material. So I was just wondering, would you be able to do any kind of weldings or just you can use fasteners because
For the connection of two
Yeah,
sections
yeah.
together. Yeah, so we can do welding together, but the fastener is more efficient. So we have now this automatic machine that can do the fasteners very quickly. So at the real application, so welding is more hard to do. So they are using these fasteners that more efficient and more less labor intensive.
Okay, thank you. There is one question on the online chat. So they say, thanks for a great presentation. Is this type of CFS best suited for dynamic loading applications? How does it perform under static loading conditions?
Statical conditions. For static, we have don't have that much problem. So because it's we are using these panels, so we are putting together very near to each other. So for gravity loading, it's okay. But for the seismic, still it's have the research area that we should provide more safety and for the application of these buildings in real seismic areas.
Okay, thank you.
Just another question.
Yes, please.
What informed your decision to go for the shape of the sigma section that you went for at the end?
So you mean the sigma sections?
Yeah. Why did you select this particular geometry?
For that one, for sigma section.
Yes.
Yeah, because based on the research and also the critical local buckling investigation, so when I applied the same loading conditions for both three sections, so the sigma was in more higher capacity than the other two U and C sections. So this was a reason for that. So because it have this web stiffening web at the middle, so it can improve the local buckling of the section.
I see. Okay. Thank you.
I have a follow-up question, if I may. Well, thanks for the presentation. First
You're
of all,
welcome.
congratulations for the research campaign. Are the sigma sections, do they have the same thickness as the previous ones?
No, it was 1.8 and the U section was 1.5. So it's
So
near
it's not,
each other.
yeah, but it's not directly comparable, because my question was, can you confirm that the sigma section with the stiffness behave better?
Yeah,
But
yeah. For sigma columns, actually we didn't get the actual failure of the element. So it was the problem with the connections. So we didn't decide yet that it's how it behaves like in this condition. But according to this critical loading of local buckling, so it's more stiffer than the U and C sections. And have more capacity, around 400 kilonewton compressive capacity in the C sections.
I was a bit concerned about the fasteners.
Yeah.
So talking about the fasteners, when we analyze those in finite element analysis, then the stress produced around the fasteners may lead to the shear failure or the tension failure. So will that be considered if we apply the loads, and how like you have told like local buckling was occurred when even the fastener were used. So is that like due to the fasteners itself, or like fasteners are reducing the shears and tensions?
So which fasteners? I mean, you mean the connections or the fastener joining the two
The
sections?
fasteners joining the sections.
Okay. So for the fasteners that joining, we didn't observe any damage to the fasteners. So you can see here, even the buckling happened here at this exactly at the same location of the fasteners, but there was no any tilting and anything damage to these fasteners. So the fastener just improved the unity of these build-up sections together. And for the numerical modeling, so we can take this as a rigid elements of combining these two sections of these two, like for example, C sections.
So this was only for columns, not for the beams and all, right?
Yeah,
So-
for beams, we have also this type of build-up sections.
Yeah, but at some point you told like it fails in tension and it's only good in compression. So can we use this one for the high bearing capacity beams? And also you mentioned like for earthquake we can use up to 6-story building for this one. So is that we looking for to use in beams?
Yeah, exactly. This have applications. So we have also built up beams that by combining the sections, but it's a bit different. Like there is under bending loading. So we didn't investigate the bending. We just applied the axial loading for these columns.
Mm-hmm. Yeah, that's all. Thank you.
You're welcome.
There are some questions coming in the chat. So we have one from our immediate past chair, Marco Pariera. He's saying great presentation and very interesting work, Numan. How will the results of your tests guide the next steps of your research?
Okay, nice question. So now we are in the stage of making the numerical modeling of these columns in OpenSeas. And after verifying our models based on this experimental research, so we will apply to these shear walls. So for designing these shear walls based on capacity-based design. So when we know the behavior of this cyclic axial loading of these columns, so we can design these shear walls. So this was the first research on a cyclic axial loading of these build-up sections. So we will continue with numerical modeling and also investigating more like the sigma sections by improving the connections and to look how that section behave under cyclic loading.
Okay, thank you. There are a couple of more in the online chat. So Colin is asking, are you only considering open build-up sections or also box sections due to two profiles, nose?
Yeah, okay, nice question. So during our presentation in Milan, so we have presented some of numerical modeling in Abacus, not this experiment research. So there was a consultancy from Canada. They were also interested in the experimental of these sections. So this is called open because these are back-to-back connections. So if we connect them to face-to-face, so it's making the closed sections. So in Canada, they have these applications in shear walls, and the corner of these walls, the closed section is more efficient than these open sections. So they asked us that if they can do some work together, so they will provide some funding for this more set of closed form built-up columns, not open ones. We didn't investigate it yet, but yeah, so it's also will be interesting question about these sections.
Okay, thank you. There is actually one more in chat. So you mentioned ease and speed of construction. Do you have any examples of in situ modular construction outside of testing facilities? And are there any material specifications for this type of CFS that can be used for structural design of elements?
Yeah, so we have Eurocode and also some specific designs from UK. And so they all have this CFS community in UK. So they have these design guidelines. More of these design codes are from US, Canada, and also Australia. They are using these sections. For example, this direct string method is a method from US, but in UK more is the use of Eurocode. So they have this effective weight method. So they just ignoring the parts of the section that's the local buckling will happen. So just taking just effective sections. So they are designing based on that effective weight method design in UK. But in US and Canada and this other country have this other option of this direct string method. So they just based on this experimental work. So they have this strength curves and they can predict the design strength of these sections. And recently we compiled around 1037 of these experimental work on monotonic loading. So we published our first database of these build-up columns. So it's available at the repository of University of Bristol. And we now we did the second one of the database. So we collected around 1037. So all this to improve the design methods of these sections. Yeah, so this was a bit of more information.
Okay, thank you very much. Anybody else in the room?
Hello, thank you. Very nice presentation. I have a question regarding one of the conclusion you showed where the web only took the tension part.
Yeah.
So my question is, I mean, I'm not still able to imagine why isn't the flange activated if the web is like it should if it's in a plastic stage, the flange shall start contributing to the strength. I mean, how were you able to confirm it that it was only the web who was transferring the tensile forces?
Okay. So the theoretical the material part, yeah. So the yielding stress was the 540. And when we multiply this with the gross area of the sections, so it's around 530 kilonewton of the yielding strength of the whole gross area. And when we analyze the yielding of these elements based on these three methods, we observe these three values from three methods. And also, when I multiplied the web, just the web area, not the flanges, with the calculated based on material properties, so it was 282 kilonewton based on that area. And also you can see the yielding specimen the same. So after the buckling occurs, so there is the tearing at these flanges. So the buckling now is concentrated at these top connections. And when there is just this connection on this part, so it just this web work was effective during the tension after the buckling happens. And in these areas, you can see from the strain gauges all the same tension in the flange. But as we did install a strain gauge here, based on these calculations, we can say that only this was working here. The same thing I calculated in the sigma, for sigma, also this area, because it's the same material we are using. And for the sigma as well, this part was effective during the tension load. And because of that, we have observed this very less tensile load in this tensile area. You are welcome.
Okay, thank you. Anybody else in the room? Okay. I actually have a question.
Yes, please.
A couple of ones. So there was a slide when there was a specimen that had a higher damping value than the rest. I think around like 0.35. Yes.
Yeah, this one is this element. Yeah, you're right. So this one, sorry, this one. So it's more damaged. So this one is more damaged than other ones. So this was the first element that we tested. So we increased the more cycles. So we have more cycles, like these two ones was 30, but this was 31. So it was more sufficient.
Okay, I see. Thank you. And I guess it's the overall aspiration of the project, but at some point the call from sections are going to be used, be incorporated in design codes and standards, so that can be used for seismic prone regions.
Yeah, so recently I have seen some photos from Turkey. So they applied this core form still. There was some researchers from US as well. So they took the picture that was applied in Malatya. So the city was in region, the high seismic region in Turkey, and also applied in Kahramanmaraş. They applied this for rapid construction applying. So we also have this application of CFS and flooding. So there is a consultancy, they applying this CFS by have some movable foundation. So when there's a flooding, so it can go up, and when after the flooding goes down. So it's quite efficient. So due to the lightweight, so it doesn't need strong foundations. So it can be built in the areas of the soil that have too much high strength, and that CFS can be used.
Okay, thank you very much. I can't see anything new in the chat. Anybody else in the room wants to ask anything? So, okay, I guess that's all. Thank you very much for this brilliant presentation.
Thank you.
Thank you for presenting your work that was funded by SECED. And thank you everyone for attending, both in person and online. And I wish you all a very nice evening.
So
Thank
thank
you.
you so much. And finally, we have one young attendee from high school. So Mr. Tom. So he sent me an email about asking this earthquake. So you are welcome. So we will talk after this.
Yeah, of course.
Yeah.
Of course.
Thank you so much.
Thank you.
All right.